Good evening, ladies and gentlemen. As has been said, my name is Amanda Birch, and as chair of the IChemE's Water Special Interest Group, I've been asked to give you a brief talk of 100 years of chemical engineers and water. The aim of this short talk is to give you an overview of the past, present, and a few thoughts to the future. 100 years ago, the IChemE had yet to be founded, and Sir Frederick Warner had not long turned 1 year old. In November 1912, Dr. Fowler, consulting chemist to the Manchester Corporation, was visiting the USA in relation to the pollution of the New York Harbour incident. Whilst he was there, he witnessed a laboratory experiment where sewage in a bottle coated with green algae was aerated. Back home in the UK, he collaborated with E. Mumford, who was also working in this area. And subsequently, he suggested to Dr. Arden and Mr. Lockett that similar work might be carried out at Manchester. During 1913 and 1914, Arden and Lockett continuously aerated sewage for several weeks and achieved complete nitrification. The work was then transferred to Manchester Sewage Treatment Works at Davyhulme, and in 1916 at Worcester, the first site in the UK to have full-scale activated plant was established. Arden and Lockett are generally credited with the discovery of the activated sludge process. The advantage of this process is that it required half the land footprint of the traditional trickling filter, a distinct benefit to larger towns. Remember, at this point, the local council was responsible for sewage treatment. Since that first plant, the treatment method has remained basically the same, with modifications to achieve biological removal of nitrogen and phosphorus, a testament to Arden and Lockett, but also the reality of the natural biological processes that process utilises. The disadvantage of this process, compared to that of the trickling filter, it is energy intensive. In the last 15 years, the real advance in this process has been the input of chemical engineers, using the best in control technology to improve the control of dissolved oxygen within the activated sludge process, so reducing energy usage and in improving the efficiency of the process. Moving on another 50 years, and 1961 sees the development of the first practical synthetic membrane by Loeb and Surajan at UCLA. It is the most widely used water treatment technology today, with a multitude of reverse osmosis applications, including seawater desalination, freshwater purification, pharmaceuticals, soft drinks, and sewage reuse. One might argue that the use of this process around the world has allowed populations to grow and live comfortably in regions of the world that are ostensibly a harsh and trying environment for man. Again, this is an energy-intensive process. The operating pressures for seawater desalination are in the region of 60 bar, but with the input of chemical engineers, the use of energy recovery turbines can see up to a 50% energy recovery. The improvement of membrane processes in freshwater purification has seen the operating pressures drop from 30 bar in the 1970s to around 10 bar today, which again results in a more energy efficient process. Over the last 100 years, the provision of drinking water and sewage treatment works has changed considerably within England and the UK, pushed more recently in the last few decades, one might argue, by the adoption of European legislation. The result in the UK, or England, is a privatised industry which, for all the arguments for and against, delivers. This next slide is kindly borrowed from one of my colleagues, Richard Hill, and beautifully illustrates some of the pertinent facts of the UK water industry. The industry produces roughly 7.5 million tonnes per day of product. The purity of this product is greater than 99.95%, and it's delivered to the point of use at less than £1 per tonne, before which over a dozen different unit operations are used in its production. The industry has used biotechnology for over 100 years, and in that time contributed back greatly to public health. It serves every industry, and it's the UK's biggest chemical process sector. So, that brings us from the past to the present. But where do chemical engineers go from here? What of the future? As we look to the future, the challenge for chemical engineers, as for other disciplines, will be to do more for less. What do I mean? Well, the world population is rising at an ever-increasing rate. With a rising world population, there is ever-increasing pressure on food production and hence on water as a resource. As populations grow, there is an increased pressure on land and the requirement for smaller footprint solutions. Add to this even the most minor effects of climate change, and the picture doesn't exactly look rosy. It has become fashionable to talk about low carbon economies and whether this will translate to higher or lower energy prices. The reality is world economics is already being felt on a domestic level here in the UK, with continued above inflation cost increases for electricity, gas, fuel oil, etc. This also translates into higher costs for industry and water and wastewater treatment. If we're to realise future demands with regards to the impact of world population increase, climate change effects and a low carbon economy, there is an absolute need for sustainable, efficient, low cost, low energy and low environmental impact water and wastewater processes, not only here at home in the UK, but especially in countries whose management of water impacts critically both on themselves and potentially on their neighbours. Chemical engineers have a vital role to play in developing these processes. Water is vital for life. It's scarce. We need to look at implementing water management techniques, reducing water consumption by reuse and recycling, the impacts of which will affect long-term public health, environment and sustainable development. Chemical engineers are essential to our future. I suspect the next 100 years will be more than a little challenging, but that's what most chemical engineers thrive on. Thank you.